Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today actually we are going to learn about a new data structure, and we are actually going to learn to implement a trie or a prefix tree. And if we see some of the companies where I want to get a job, who already asked this question, there are companies like Amazon, Google, Twitter, Microsoft, Oracle, Apple, Facebook, Goldman Sachs, Uber and Bloomberg. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are going to implement a trie over here or a prefix tree. So first of all, in the problem statement we are given the definition that what a trie is, and actually I'm going to show you very eloquently that what a trie is and how it works. But let's understand the definition first. Basically a trie is a prefix tree, which is a tree data structure that is used to efficiently store and retrieve keys in a data set of strings. There are a bunch of different applications of this trie data structure, and I'm going to go over all the applications soon as well. Now, if we see that what is needed in this problem, basically we need to initialize a trie object first of all. Then we need to create three different methods which are mentioned over here. So first method is the insert method, which does not return anything, and basically we are only given the input as a string word, and we need to insert this word inside this new trie object that we are initializing. After doing that, we could be given a search method where again as an input we are given a string called word, and we need to return true or false, which means that whether if this word exists inside this trie object that we have created, we need to return true, otherwise we need to return false. And there is also one more method where again we are returning true or false, and the name of method is startsWith, where we are actually given a string and the name of the string is prefix. But basically we need to check that whether this prefix actually exist as a part of any existing word inside this trie object, and if that is the case we need to return true. If that is not the case, we need to return false. So here is an example that we are given. So suppose we are given as an input where actually first of all we are creating the trie, we are inserting some word, we are searching for some words, we are doing the start with operation, and this is the explanation. So basically we initialize the trie object as mentioned. Then first of all we insert the word apple. So okay, so currently apple exists over here. Now again we search for that whether apple exists or not, and because it exists we return true as the answer. Again we search for with the word app, but the thing is, remember, so far we have only inserted the word apple. App does not exist as a whole word, so that's why we return false. Again we search for startsWith method for this word app, and remember, because this app is actually a prefix of this apple, so we return true in this case, and so on and so forth. We can do bunch of different operations. So this is what is needed. Now let's understand what a trie is. Okay, so first of all, let's try to understand that what a trie actually is. Basically, a trie is a tree-like data structure, but it's a little bit different and a different variant of a tree. Now, if we know for any single tree, the basic properties are that every single tree has a root node. Now, this root node has some subsequent children nodes. There could be n number of different children, and those children can have some children of their own, and their links actually found some meaningful relationship. So that is what we are going to use to generate this trie, but we are actually going to generate this trie to store different string values per character. That is the important property, per character. So it makes us easier to understand or find different words or different strings, and there are n number of applications of a trie. Let's try to understand trie with some example. So first of all, as any different tree, we are actually going to have a root node, right? Now suppose for this root node, what we are trying to do is we are trying to add some different string value. So let's take a string value. Suppose the first string we are trying to add is actually the word FAANG. So if we take this word FAANG, first of all we will have to add the word F, because remember I already told you we are going to do it character by character. Then we will add A, N and G. We are going to add it in this sequence. So in order to do that, logically speaking, for this root is going to remain common. But the thing is, first word we will have to add is FAANG. But the thing is, first we will check that whether is there any children of this root node which is actually F. If that is the case, we are actually going to leverage that. But this does not have any children. So if this does not have any children, we are actually going to create a new children F. Now again, with this F, there is no children, that is A. So again we are going to create a new children, then again we are going to create a new children, and then we are going to add the values of N and G as well. After adding this, we have actually created a root inside this trie data structure which represents this word FAANG that we were originally trying to create. After creating that, we will have to find some way to identify that this FAANG word has actually ended. So what we are going to do is we are actually going to create a special character or a special node over here, which we are going to denote as an end node, which defines that the word has actually ended over here, right? After doing that, let's try to add one more word. So suppose rather than FAANG, we are trying to add the character MAANG. So let's try to again add MAANG over here. Now for this MAANG, first of all, we are going to check that whether this M exists as one of the children of this root node. So M is also no children. So first of all, we are going to add M, and then we are going to add subsequent characters, and we are going to link them with this path. After that, in the end, we are actually going to add a special character and denote that the word has actually ended over here. So let's do a quick recap. Basically what we have done so far is we have actually created two separate branches, where if we go depth first search diving in those branches, we would actually find those subsequent words in those particular branches. So it makes pretty efficient for us to identify any string and to see that whether it exists or not, and predict that what the person is going to copy. Now suppose I'm trying to add the next word fan. Now for the adding this next word fan, what we are going to do is first of all we are going to check f exists or not. So f exists over here. So because f exists, we are actually going to leverage that. So now we are not going to add any entry over here. Again, this a also exists as one of the children of f. So again, we are not going to add any entry over here. Now this n. So n is not a children of this original a. So we are actually going to create an entry over here. So we will create an entry over here, and we are actually going to name it as n. And now since this word ends over here, we are actually going to create this end node over here. So again, remember, if we go depth first search in this direction, we will actually be able to find this word fan, and that is the whole purpose of a try. Now let's try to add one more word, which is man. Sorry, M-A-A, ma. So if we try to add this word ma, so first M also exists over here, A also exists, and A also exists. So because these three exist, we are actually not going to break this link and create this end word over here, or we are not going to do that. Actually, we are going to keep this as it is, because this MAA is actually a prefix of this original word MAANG that we have already added to our try, and that is why a try is also called a prefix tree. So now the word makes sense that why a try is called a prefix tree. And basically this is what we are trying to implement. There are a bunch of different applications of a try, and let's see some of the applications that are really cool in real life world. So before we start implementing the method, first of all, let's understand that what are different applications of a try. So applications like autocomplete, where you type something and it automatically gets completed or understood by that particular product, that is implemented using try. So features like Google Chrome, Amazon, where you type few words and then it automatically understands that what you are trying to do and automatically gives you the answer, that is implemented using that. All the spell checks or all the dictionary related mechanisms, they are also implemented using some versioning of a try. Games like word search, word puzzle, wordle, they are also implemented using a versioning of a try. And features like predictive text search or expected text search, that you type something, it automatically expects that what could be the next potential words. Typically you see that in YouTube, Google all the time. They are also implemented using tries. So these are only few but very powerful applications of a try, and there are hundreds of them. I haven't mentioned them. So that's why try is important to understand. Now let's move back to our question and start implementing those three methods. So first method they are asking us to implement is an insert method, where we are not returning anything, but we are inserting different strings into our try. So for this example, we are actually going to implement these 4 different types of strings into our try, and we will see that what would be the logic behind it. Now, as mentioned earlier, that every try actually has a root node. So again, with our try, we are also going to have a root node. Now from this root node, the idea we are going to use is that whatever string we are trying to insert, first of all, we will check that whether the first word that we are trying to implement or the first character we are trying to implement, if that is present as one of the children of the existing root node or not. If it is children of that particular root node, we would keep on branching for that particular child and keep on updating the number of characters that we are trying to implement. If it does not exist, we will actually create a new node or a new branch, and we will add that entire word into that branch. Now, as mentioned earlier, the moment we reach to the end of that particular node, we will actually have to create an end node to denote that this word actually ends over here. So let's start implementing what is being asked over here. So first we are trying to implement the word apple. So a does not exist as any of the children of this root node. Currently it has no children, so we will have to create a new node. So first we are going to create a new node for apple. Okay, so let me create a new node a, and then I will keep on appending all the remaining characters. And after adding all the word, because this word ends at this e, I am actually going to create a special node and I'm going to denote it as an end node. So that is to for us to understand that this word actually ends over here and we don't need to move any further. Okay, now next word we are trying to implement is G. And also remember one thing, I forgot to tell you that this root can have potential 26 different children, right? And this 26 different children can have 26 different children of their own. So the mechanism we are going to implement to find that whether a node contains any particular children or not is actually going to be used based on some key value mechanism. And because it's a key value mechanism, the whole operation of searching that whether any node or anything, if that is part of any children of that particular node or not, that is being done in constant time, so that it helps us understand, helps us to maintain the consistency and speed of our data structure. Now let's move back to adding the word Google to our try. So for the word Google, we do not have any children that is starts with G. So we are also going to create a new node over here or new branch over here where first character is G, and then we will add all the remaining characters. As previously mentioned, at the end of the word we are going to create an end node. Okay, now things become a little bit interesting with this word Amazon. So for this word Amazon, when we start checking that whether this a is a children of this root node or not, we find that a is already a children. So we will keep on updating the value over here that okay, we have already find a word or a character that is already a children, and then we will keep on moving to the next character. So first this a is already present, so we ignore that. Now next character we want to find is M. So for this M, we will try to see that whether this a contains any children that starts with M. But the thing is, currently this a only contains one children that starts with P and not M. So we will have to create a new branch over here. So let's create a new branch. So new branch starts with M, and then we will add all the remaining word characters over here. Okay, and now the next word we are trying to implement is amazing. For the amazing, okay, we already have a children of this root that starts with A, so we have taken care of this. M is also present as one of the children. Okay, now A is also present as one of the children of this M. Okay, so that is also good. Now this Z is also present over here. Now for this I is actually not present as one of the children of this Z. So we will actually create a new branch over here that starts with I, and then we will add this N and G over here, and in the end we will create, or we will add the end node over here. And now we have actually inserted these four characters as or these four strings into our try, and if you see, we can find each one of them by going in DFS motion in any particular branch. So first of all, this gives us the value Google, this gives us Apple, this gives us amazing, Amazon, and this gives us amazing. So that is how tries typically work. Now let's move on to the next method that is being asked. So for this search method for our try, we will be actually given a word as the input, and we will have to check that if that word exists inside our given try, we will have to return true. If it does not exist, we will have to return false. So let's start implementing the same method, and actually we are going to use the same try that we have created. Okay, so let's use the same try that we have created earlier, and we will try to see that whether these four strings do they exist inside this given try or not. So let's understand the logic behind it. Well, if the string exists, basically all we will have to do is, first of all, we will check that okay, whether the first character, if that is the one of the children of this root node or not. If that is the children, we would keep on checking its children for this next subsequent words and try to complete this entire word. If we are able to complete this entire word without this try breaking or not able to find the children, if we reach to the end, we can conclude that this word exists. If we cannot come to the end, we will conclude that this node does not exist. So first of all, let's try to see in this example. So for the first word is A. So A exists over here as one of the children. So we will ignore this one. Now next word is M. M also exists, so we will again ignore this one. The next one is A, again this word exists. Now Z, I, N, G, they all exist in this particular fashion. So this word amazing exists inside this given try. So because it exists, we will return true as the answer in this case, right? Now let's try to search for this word good. Now for this word good, the first character is G. So first character is G present over here. So okay, we are good up until this point. Next character is O. O is also present. Again, O is also present. So we can ignore first three characters of this good. Now for this next O, we do not have a children that starts with value D. So because of that, we do not have any new branch over here that starts with D. So we can actually conclude that the word good does not exist in this case, and because it does not exist, we will return false over here. Okay, now let's try to search for the word googler. So again, for this word googler, okay, G also exists, O exists, O exists, G exists, L exists, and E exists. Okay, up until this point all the words exist, but when we try to search for the next word, we actually encounter that okay, this is the end node of our try or of our DFS search for this particular direction. So because it is the end word, we will actually return false over here, because this word has not been completely searched, because it does not exist inside our try, and we are actually able to do it pretty quickly and pretty efficiently. Okay, so now next word is app. So let's try to see that whether this word app exists inside our try or not. So first of all, we check for this word A. A exists over here. Then this word P. P also exists and P also exists, right? So we are up good up until this point, and our mind will say that okay, because this word exists, we need to return true. But the thing is, that is not the case. The idea we are trying to do in this search method is that we are trying to see that whether the whole word that is given as the input exists as only a word inside this given try. But for this app, if we try to see the next node is actually the SL and E. So there are still some characters that exist inside this given DFS path that we are traversing, and the next node is actually not the end node. So because the next node is not the end node and there are still some more nodes that exist, this app is actually a prefix of original word apple, but not the whole word as it is. So that's why in this case we need to return false as well. And this is the important thing that is differentiating between this method, search method, and the next method we are going to implement. Now if we see the time and space complexity, in this case the time complexity for this method is actually going to be big O of n, where n is the number of characters that are present that we are trying to search in any given word. If we see space complexity, for the space complexity we are actually not using any additional space, so that is going to be the constant space complexity for this case, which is pretty efficient in my opinion. So now let's understand our starts with method, and we are also going to use the same try that we have created before, right? And we are going to see that whether the words that starts with these characters, are they present inside our given try or not. So again, this is very similar to the search method, where we are going to iterate over word by word or character by character for any given word, and we will see that whether that is present inside our try or not. If that is present, we can return true. If that is not present, we will return false. So let's see that in action. So first of all, we have this character A. So A is already one of the children of this root node. So okay, we are good up until this point. Then we have M. M is also a children over here, and then we have A. So A is also a children of this one. So we can conclude that because this word ended, we do not have any more things to search for, and all of the characters, they were present inside this given try. We would actually return true. In this case, they are saying that the word that starts with AMA is actually present as one of the children or one of the branches of this try. Now let's try to search for this word APK. So A exists and P exists, but the thing is, for this P we do not have any children that starts with K. So because of that, this K is not present. We can actually return false in this case, saying that we do not have a word that starts with APK as the prefix inside our try. And remember, because we are searching through prefix, that is why this is also called prefix tree. So yeah, mind blown, right? Mine as well. Now let's try to search the word good. Well, there is Google, but there is not good. But the thing is, Google is pretty good. Yeah, so that's why it's one of my dream companies. But let's try to search that. So okay, this is GOO. So GOO is present over here, but this D is not present as one of the children of this O. So because of that, we will also return false in this case. Okay, now we have this word apple. So apple is actually the entire word that is present over here. And if you look at it, we do have a word that starts with the word apple, even though it ends at apple. But the thing is, also it starts with apple, right? So, and the name of the method is actually starts with. So why should not we return true in this case? So this will also become true, that okay, word that starts with apple is present inside our given try. And that is the logic we are going to use to implement the starts with method. Again, very similar to the search method, just a little bit different variations. Now if we try to see the time and space complexity, in this case the time complexity is also going to be big O of n, that is where n is the number of characters that are presented inside any word that we are trying to search. If we see space complexity, the space complexity is also going to be big O of 1, or constant space complexity, because we are not storing anything in our text stack. This problem is asking us to implement insert, search, and starts with method. But before implementing these three methods, first of all, we'll have to define that what a try node is. This is only a try class. So I would be creating a separate class called try node. Now in this try node class, first of all, let's go over some basic methods that we are going to use that will enable us to do a lot of things. First of all, we have defined a finite number of cases R, which is 26, because any single node can only have up to 26 distinct children, because each children represents a character inside the alphabet. Now every single try node has a certain set of links, and links are defined by the children of that particular node. We also created some more methods, so let's go over them. So one method is contains key method, where we pass in a character and we get the answer that whether any particular link or any particular node does that contain that particular character as one of its children or not. And we can get the answer in a constant time complexity, because remember, we are using array indexing, and the maximum possibility of indexing can be 26, and we can get the answer immediately. Same, we have a method get, where we provide the character and we get the answer that whatever the value of that particular character is inside any of the children of any try node. We also have a method put, where we provide the value of a character and the node we are trying to put it as. And we also have set end and is end method. That is to define that whenever we run out of words that we need to put in any single try block or any single try branch, the last node is going to be is end node, and we will mark its value to be true. So now let's start implementing the try node. So first of all, we will have to create a try node root. So let's do that. Now since we have our root node, first of all, for this public try method, we are going to initialize the root. After doing that, first of all, let's start working on our insert method. So for our insert method, we are going to have a root node. Now we are going to iterate over the given input word. We will define that what is the current character we are at. Now first of all, we will have to check that whether the given node we have, if that contains that particular key or not. So if the given node does not contain that key, we will actually have to create a new entry over here. So we will use our node.put method, and inside that we are going to pass in the value of the current character, and we are going to pass in the we are going to create a new try node for that, and then we are going to update the node's value. And once this loop ends, basically the last node we are at, we will have to set its value to be the end node. So we are going to mark its value to be the set end value, and which would basically, so it defines that this is the last node. Before we work on the search and starts with method, remember, both search and starts with method, they are pretty similar to each other. So we are actually going to create a supporting method called search prefix. Once again, we are going to initialize the node to be the root node, and now we are going to iterate over the given word. So now we are going to check that if the current node, does it contains the given character or not. If it contains the given character, we can actually set the value of node. If it is not present, we simply need to return null, and that's it. And if we somehow reach to the end of this loop, we can simply return whatever the node we are at. Now from this our search method, basically what we are going to do is, first of all, we are going to initialize our try node, and we are going to pass in the value of the word. Now we simply have to return that whether the current node we get in the return, and if it is not null and it is end, we can simply return true. And same thing we are going to do for our starts with method. So again, for our starts with method, we are again going to call the search prefix method, and basically all we will have to check that whatever the return value we get, if that is not equal to null, if that is not equal to null, we can simply return true, and that should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. and our code runs pretty efficiently compared to a lot of other solutions. And it is also very much efficient in terms of space complexity. The thing is, I was not able to come up with this solution on my own. I actually had to use a lot from the solution tab. So I just want to make it clear. So yeah, everyone has to go through it, and I would be posting this in the comments so you can check it out from there. Thank you.